Oh, sweet, I'm live. It's cool that the first 20 seconds of this will just be silence. Top-down camera not working again. And I have real analysis class at 2:50. So like an hour, but I gotta get up there. So this will probably be a short stream, but ideally I show back up later. Alrighty. Silence off. Lori, nice to see you here. Alright. I was thinking, so last time I was kind of involved in this question. B, I guess. I was involved in GCD. A to the Bn is GCD. Well, we want to show that exponentiating these is also whole. Oh, what's up, Johnny? Wow, you sniped this stream quickly. I was like looking at let's see, trying to build more intuition for the GCD, and yeah, Johnny, in just a sec, if you want to hop on a call, I'd be down. But I was thinking about the GCD and like what actually is the GCD, because I don't know, I feel like I could have better intuition for it, and I was thinking like it's actually like 3 separate components. It's like if you're given a number, take the set of all divisors of that, and then you do that for 2 things, and then you basically take the intersection of those 2 and then take the maximum of the intersection. So it's basically like well, this g function is pretty much just a max. It's like max common, or max of like the intersection. Actually, I can simplify this even more. Of the sets of divisors of 2 different things. Oh, hello from Brazil. Yeah. So I wanted to think about like GCD A and B equals 1, or them being coprime, is basically saying that the intersection of their divisors, the maximum is 1, which means that in fact it is just 1. Like the intersection of their divisors is just 1. The max doesn't necessarily really matter, I don't think. And then I also wanted to look at like what are the properties of the just plain divisors, which I don't know, maybe this is a little weird, but so say that you have like 2 variables. I wish I could draw on paper in this, but my camera's broken. So you have a variable and it's got a set of divisors. Oh. Yeah, that's exactly it. The nice thing about is the Euclidean algorithm gives you a ridiculously fast algorithm to compute it without calculating all divisors. Yes. So what I'm interested in is like just the general divisor function. Like how does that behave under certain operations? Like, so if you've got the divisors of A and then you have the divisors of B, what happens like if you multiply 2 things together within a divisor function? Is it like the union? Does this equal like D A union DB? Just like to think about a oh, note that 1 is a divisor, then -1 is as well, so you do need the max. Okay, yeah, good point. Yeah. But I just think that's interesting. Like, if you think of all numbers as having a set of divisors that kind of are like the component parts of them, then what happens to their divisor representations as you multiply the two numbers together? I would guess like the two sets just get added together, because it's like all factors, all the factors of one plus all the factors of another. But what's interesting is like, say that like a equals 3, b equals 2, for instance. So what we would get for divisors of a would be just 3 and 1. And then divisors of b would be 2 and 1. But it actually can't be the union, because the divisors of b times a would be like 1, 2, 3, 6. You would also get, there's like an additional stuff that gets added in. Yeah. Yeah, which is really interesting. And I would just like a kind of intuitive way to look at that. I don't know. Yeah, and I just think that would help me in understanding this proof, that the GCD of, like, how I need a better understanding of how the component parts of a number kind of work out. Yeah, it's I mean, I guess what's clear is like the union of the two different sets of divisors is a subset of the set of divisors of the product of the two numbers, which means that everything that divides A and everything that divides B divides the product of A and B, which is obvious, but yeah. All right. And there was like a hint off of last time too, that currently on, I wonder if there's like a nice way to like highlight the current question. we're on 5. I'll make a function to do it. Current. Actually, let's have current take content, and then let's go current, and then it, and then text red it. We can make that cooler too. Current use Emacs, you poor man. I am gonna switch to Emacs at some point, I think. Just because like I need org mode. My friend keeps trying to get me on Obsidian, but like Obsidian is too I can't stand Electron. Alrighty, so this is relying on the fact that the divisors of A and B, greatest common divisor of A and B is 1. And there's a fact we showed last time. To stay organized, duh. I think it was like 2.5 question 20. Well, actually, I don't especially want to look at that. Yeah, there's a certain property here of, it's this one. This is number theory. D divides A, D divides C, implies D divides A plus B minus A. No, it's 20A. So, set of divisors of A, set of divisors of B, the biggest one of those is 1. And then the set of divisors of A and C, the biggest one between those is also 1. And then the set of divisors of A and the set of divisors of those two things multiplied together also being 1. I'm trying to think about, like, intuitively, that's just saying, I mean, so we're getting, by multiplying these two things together, right, we're getting a set of divisors for, we're getting the set of divisors of B, the set of divisors of C, and then they're all added together, and then there's an additional set of divisors of B, C. And in that additional set of divisors, we didn't find anything greater. Interesting, interesting. Yeah, number theory is really, really cool. I like it more than analysis, I would say. But I don't know, analysis has its merits too. It's just number theory is like really mind blowing because let me go back to the equations. It's like there are just so many damn patterns to the numbers you wouldn't think. It's like they're kind of innocuous. It's like, oh yeah, 6 times 7 is 42. All that kind of stuff, but like there's all the ways numbers multiply together and combine are all like have been analyzed very meticulously, and it's all there's just crazy patterns to it all. Or I don't know. There's some questions that just like blow my mind. Like this one down here, when I was writing it out, every integer greater than 1. Oh, you cannot see that. Let me put myself up in the corner, maybe. Every integer greater than 1 is the product of a square, free integer, and a perfect square. Like, that's just so bizarre that that's true. Or it's, yeah, I don't know. There's a bunch of things like that that's like, you would never think to look into it, but there's just hella patterns underneath. Yeah, I'm excited. All right. And I guess we're given, it's kind of weird what we're given and what we're not, but so the current, if A and B are co-prime, then they're any powers of either A and B are co-prime. Yo, what's up, Vladimir? Thanks for the euros, my guy. Yes, we still on that question. Generic looks maxer. I want to make sure I really understand it well. And using that theorem from yesterday, which is just that. I see how to do this, I just want to write it out rigorously. And no, you cannot buy entrance, unfortunately. I because that would be weird. That would be like pay to win. Plus, I feel like it would be a weird vibe, you know? You offered to buy my OnlyFans. Bro is scamming people? What do you mean? What do you mean scamathy? I don't know. We're figuring out the Discord entrance. It's creating a Discord that's like actually worthwhile to be in is tough. So we're like very slowly admitting people. If like at all, it's like slowed to a crawl right now, and we'll continue to let people in over time. But yeah, right now we're keeping it stable as is. ETA on email answers is like whenever I have free time, which is not a lot these days. All right, I'm gonna hop on a call with Johnny.
Yo, what's up?
Hey, how's it going?
I'm good, man. How are you?
Good. Just dealing with some bribery in the chat. Just par for the course, I guess.
Yeah.
Get what you get if you stream. Yeah.
Yeah. I'm really curious who this person actually is. If they are who they pretend they are.
Yeah, I mean, if he drops 10 grand right now, we'll see.
If he drops 10 grand, I mean, you can buy my OnlyFans. No worries.
Yeah. All right. I don't know if you're currently watching. I'm working on GCD A B equals 1, implying GCD A to the n B to the n equals 1, and
yeah. I was yesterday also in the stream, right? I didn't watch this. I just was there at like the very very end, just before you ended. Did you manage to do that one yesterday or no?
I mean, I got the broad strokes of it, but I haven't like put it down into a rigorous proof yet. And as I understand it, it's basically just induction, and there's like just this lemma you use to show that. But
is that the dilemma which is like directly under the red line?
Yeah, it is. The yeah. Which is, I guess I see. I mean, the proof of is just you turn it into like linear combinations, and then you can factor in an A, and then you've got and a BC, and then you've got that GCD.
Yeah. I mean, yeah. I think that will work. You have to do like, I think like induction twice or something technically, or maybe you can do it in one. It might be slightly awkward, but I think that's a good way. Especially because you said yesterday you can't use anything like related to prime numbers, right?
Right. Yeah. No. Yeah.
Yeah. Then this seems like a good strategy. So, do we take this lemma for granted for now, or did you need a proof of it?
I guess we can take it for granted. It's pretty similar or pretty simple to prove, I think. All you have to do is like turn both the GCDs into linear combinations and then multiply them together and then factor out
Yeah, okay. I can believe that. I can see that from with the Bernoulli. Yeah. And I
Yeah.
think this is the identity.
Yeah.
Yeah.
Um,
Okay. Yeah. Okay. I think if you have this lemma, then I think it should be. Well, I don't want to say straightforward, but there's like shouldn't be much more algebra involved. It will just be like actual like proof step in induction.
yes. Um, and is this a case where you could use without loss of generality because you could just prove like um, you could prove one side of this and then just say either argument to the GCD could be used.
Well, what exactly do you mean by one side of this, right?
I guess proving that like b to the n implies b to the n plus 1 or only imply one component because the lemma we're given is kind of it's like one-sided, I guess.
Yeah. I mean, yeah, you have to say like the GCD is symmetric. Yeah, if you mean just that you can use it like in both components of the GCD, I think you can just say like I have this lemma, the GCD is like symmetric. can like flip the argument around, and then I have the lemma for the other argument. If that is what you mean.
Right. Yeah. Yeah. Yo, thank you for the $50. That's an outrageous amount of money to drop on a guy refusing all your
Yeah.
offers, dude. I'm not exactly sure what your
Also, he's doing it all in euro, and it's suspicious for a Russian oligarch. Not gonna lie.
is that not the currency? I guess they're not part of the EU.
No, very much not. They have the ruble. I don't even know what the symbol is, but that's not it.
Yeah, that is suspicious. Yeah.
Yeah.
Um,
I mean, but maybe you can drop another 50 just to be sure. Maybe I was mistaken. Maybe it was the ruble after all.
Trying to bait him into yeah.
I live in Germany. Suspicious. You can't define GCD without prime factorization. That's not true. You can define a GCD as literally like what the acronym is for, the greatest common divisor of the two numbers.
Yeah. All right.
So, okay. So I think what you can show is that if you have, with this lemma, you can show that, suppose that GCD A comma B is equal to 1, then GCD A comma B to the n is equal to 1. Right? And this is indeed by induction.
If GCD.
So,
yeah.
I think when you write it like this down, you should clarify what exactly you're going to prove by induction, because we're not technically yet proving like the whole statement that the exercise wants, right? We're only going to do it like in between steps.
Right. Yeah. I see.
Also to help yourself, like what we're trying to prove.
So proceed by induction on n, and we want to show that just kind of rehash the statement that and assuming GCD AB I've seen I don't know the template for induction written something like base and then inductive step, but
yeah, I mean, yeah, you don't, yeah, usually, I mean, you always have to do a base case, and an inductive step, you don't have to like write out like with so clearly. I think as long as it's both there, you don't have to. I think like differentiate or like explicitly state which is which. I think the reader can kind of do that, but it's fine. It helps, like maybe in writing the proof first with like clarity.
Yeah.
But I think we first want to do this. We want to do this induction proof only when we have like one power to the n, right? We want to show that if the GCD of a comma b is equal to 1, then the GCD of just a and b to the n is equal to 1. Because
Right.
that's what this.
That's what our lemma gives us. Yo, thank you for the €40, Vladimir. This is not a good way to spend your money, just in my opinion.
Crazy.
Yeah, for real. The base case, you would say n equals 1, and we just...
Yeah, and well, that's kind of by assumption, right?
Right.
So, I guess maybe to make it even more clear, right? You have now in your bottom line assume GCD implies GCD something else.
Yeah.
Well, we just want this assumption, right? We don't want to assume the whole implication.
We
You
just
know what I
want
mean?
the...
Like now it seems like you're assuming that the implication is true, but we just want to assume like what's in front of the arrow.
Oh, yes, I see. Yeah. That's all we have towards... Yeah.
So you can put this assumption even before you have your base case, right? Because this is what we're assuming before the base case starts. And in the inductive step, we'll make some other, like these what do you call it? The inductive hypothesis is some other assumption.
I see. Okay. I see what you're saying. Yeah.
Yeah. So indeed, the base case is literally just done. And then so for the inductive step, we're going to assume that the statement is true for some fixed value n. And then we just have to prove it for the next value.
Right. But we're just doing it on one side.
Yeah, and you'll see afterwards. Then the other side will be kind of for free.
Right. Well, we actually...
b to the n, right? You want to assume in your inductive step.
n plus 1, you mean?
No, I mean now it says assume GCD a comma b is equal to 1. What we already did before. We don't need to assume that again. We just need to assume that GCD a comma b to the n is 1.
Okay, yeah.
Exactly. And now we need to prove that GCD a comma b to the n plus 1 is true.
Right.
Or is equal to 1. And for this, this is basically like one application of our lemma.
Right. Which we can do as, since we have, this is very straightforward. Since GCD A B equals 1, and we have that assumed step, all we have to do is say that GCD A B times b to the n.
Yeah, exactly. Like, and you see, like, kind of writing it down carefully, like putting down at each point, like where you assume what, kind of already helps you with seeing like how the proof should go.
Yes. And then
exactly, and this is basically it.
To the n plus 1. Okay. By assumption.
I think in the second to last line, you want to remove one of the b's. I think it's double.
I want to remove one of the what's?
The b. And like you have b to the n, right? It should just be b to the n.
Right. Yeah. But yeah. And it seems like by assuming that lemma is like just doing 90% of the work, which is like, I wonder if my teacher actually wants to show the expansion of stuff, but
What do you mean? Like,
um,
what kind of?
like the proof behind why this lemma holds. Although I don't know, because it's just like given in one line.
I mean, I don't know. I don't know where it comes from. Did the teacher give you this lemma, or what did he say?
He said, like, let's see. There's a hint. He said refer to the hint section, like 2.4 or 2.3 maybe 20. Yeah, right here, which is just it's interesting. This is pretty much just given.
Yeah.
Part A of
It's
20.
it's literally just the proof in the hint.
Yeah.
That's crazy.
Yeah, I mean, I guess
I mean,
Bezout's lemma is applied like a couple of times, but
yeah, you just have Bezout, and that's it.
yeah.
Okay. Yeah, I mean, if you didn't say anything, I mean, if you hand it in, I would say, like, refer to this, where this lemma comes from. Like, by exercise 20.a from this and this, we have this lemma.
Right. Yeah.
And then I guess if you want to be really nice, like in your proof, you should mention at which step you apply the lemma. So we have since blah blah and blah blah, we may conclude from the lemma or the exercise that, and then you're fine.
Right. And is this like a double induction, or could you just say?
We can get away without a second induction now, because now we've proved one statement, right? We have that we have two coprime integers, so GCD equal to 1, and then you can raise 1 like to the nth power, and it's still coprime. But now if we reverse the role, so b to the n will take the role of a, and a will take the role of b. Again, because the GCD is symmetric in its argument. Yeah. We can from this proof, we may directly conclude that so I guess we have to conclude in 2 steps. So first we say because a and b are co-prime, then a and b to the n are co-prime, but then b to the n and a to the n are co-prime, right? So you just do it in 2 steps, but you only need this induction proof once.
Right. Yeah, I see what you're saying.
You need to prove it once, but this result from this induction proof, I guess we apply twice in that way.
Right. Could I just say, like, because GCD is symmetric?
Yeah. We conclude blah, blah, blah. I think you can first kind of conclude your induction proof to say, because this induction is kind of like a proof within a proof, right? We've first shown this result, that you can raise one of the arguments to the nth power, and this kind of mini result, this mini lemma, we're applying twice within our proof.
Right.
So it's nice to say, like, once you're done with the induction, to say, by induction, we now know that, like, the implication is true. A comma b co-prime implies a comma b to the n co-prime. And now we have proven this, and we apply this twice because GCD is symmetric, yada yada. Yeah.
Right. Okay.
By the way, to the person who said a while back in chat that you need unique factorization to have a GCD, that's not true. You can have also in rings, you can have a GCD domain without being a unique factorization domain. But anyways.
Yes. All right, and
yeah, this looks good.
This question is interesting, and it's weird because we kind of, well, never mind. Yeah. A to the n dividing b to the n implies a divides b.
Let's see. Yeah, okay, again, without prime numbers.
Yeah. Yeah, without, this seems like a very primitive thing. Without prime numbers.
Yeah. Let's see here. I mean, yeah, again, if you can use like things about prime numbers, then that would be very easy, but they want something else.
Yeah.
I guess, I mean, the kind of thing you want to show is like, right, a to the n divides b to the n. That means there is some integer k, such that if you multiply it by a to the n, you get b to the n. And what you want to show is that this k must be, again, an nth power of some other integer. And then what it is the nth power of, that will be your multiple of a that's next to b.
Someone said, never mind. This seems like just pretty,
yeah. It feels, I don't know, to me, these things feel obvious, but like kind of that makes, sometimes it makes it hard to prove it, right? Because like all the things you want to say, obviously true, you can't use it. You have to come up like with an actual reason. Reason.
Right.
What kind of other results have you seen so far? Like just been GCD stuff. Maybe we can use something.
Some kind of GCD thing. Yeah, I mean, we have seen a lot of the properties of GCD. I guess.
Like, it's probably not very helpful, but like because we've seen so much GCD stuff, like this kind of thing feels like, or my first thought is to express these conditions of divisibility into something relating to the GCD, right?
Yeah.
So the first thing that comes to my mind is that like A divides B for any two numbers exactly if the GCD of A comma B is just equal to A.
A divides. Oh, yeah, yeah. I see what you mean.
So then you can phrase it in terms of a GCD equation. Is it going to be helpful though? I don't know.
I wonder. I mean, I guess worth a shot. So GCD of A and B, or well, we have A to the N, B to the N, equals A to the N.
Yeah, so we're given that. Yeah. But for that, yeah, we've before only really seen things about GCD equal to 1.
Yeah. I mean, isn't this... I'm also just thinking, like, what we have here, isn't there some way to factor this out so that we just get a definition of A divides B? Like, you could... I mean, like, this seems really obvious, but couldn't you just say, like, this is the same thing as A times A to the N minus 1 times K? And this is the same as B to the N minus 1. I mean, that I'm just I'm not sure what I'm allowed to do here exactly.
Yeah, no, I get that. I mean, you can say this, but this will only give you that, for example, yeah, you can conclude that A divides B to the N, but this is something weaker than saying A divides B.
Why does that only give us that it works for B to the N?
If you wanted it for B, you would need to write like some product equals to B, right? You need A times some integer actually equal to B.
Right.
It's not sufficient to do it for multiple of B.
Right. Yeah, I see. That is weaker. Yeah. Yeah. Tough that we can't use primes.
Yeah. Or maybe induction again.
That's an interesting idea, actually. Yeah. I guess it's worth a shot.
yeah, for example, can we do the n equals 2k easily? I don't know. Before we do like the whole induction setup.
Right. Yeah. I mean, yeah, the n equals 2, so a squared divides b squared. Oops. E
Yeah, I'm thinking about it. I think
Do you think this is going to be some kind of GCD property? Because
okay, yeah, I feel like I have an idea of maybe for the general case, and we're a little bit metagaming it, as in like these problems were put one after the other for a reason, right? Is my guess. So my guess is that we'll probably have to use problem A.
yeah,
in
could
here.
be. Yeah.
So we want to somehow cook up some numbers which have GCD 1. And I have a slight, yeah, I think I know what's going on. So, yeah, and I think, I think we want to use indeed this fact about like this division you exactly have when the GCD, when like the GCD of A and B is actually equal to A. I think we can show this. Yeah. Okay. So if you write A to the n, or sorry, no, other way around. If you write like, we give the GCD of A and B some name, right? Let's call it D.
Okay.
And we want to show that this D is actually equal to A. Then we're pretty much done. Maybe I think up to some details. If we can show that thing is equal, D is equal to A, then we're good.
And are you talking about to the n, or just?
Sorry?
Are you talking about A to the n, B to the n, or just A, B?
I'm just talking about A, B, right? Because we want to show that A divides B. So yeah, exactly.
Yeah.
Let's see. I hope it's gonna work. Want to show that D equals A. We can write now A as some multiple of this D, and B again as some multiple of this D, just because the GCD divides both of them. Right? You give these like some names.
D is some multiple of
yeah, as in like you can write A as K times D and D as L times D.
Oh. Yeah. I don't know what I was thinking. Yeah.
Right?
Yeah.
Yeah, exactly.
Yes.
And now I think we can say, because now we should argue that these K and L, this pair should have GCD actually equal to 1.
They're co-prime. Yeah.
And there we can apply our problem. So this is like my strategy.
Okay, yeah. Yeah. And why? Oops.
Why what?
Why is the GCD, or I guess we're about to show that, if K and L equals 1?
Yeah. I mean, this I think we can just show from the definition, more or less. As in, suppose that it was bigger than 1.
Yep.
Then we have some number which divides both K and L.
Yeah.
And therefore it divides A and B. But then if you multiply that with your D, this product also divides A and B, but it will be bigger than your GCD. So because our D is already our biggest divisor of them both.
I see. Yeah.
K and L.
Yes. Yeah. Okay.
So yeah. So
yes.
because GCD, because the GCD of K and L times D must divide both A and B, it must also divide D. So then that better be equal to 1.
Yeah. Oh, divides D. Yeah.
Exactly. Well, or if you write it like this, you should say that the GCD. The GCD times D divides both A and B, and therefore the GCD times D divides D itself.
The GCD.
And that's because otherwise, I mean, it's not immediately clear why this GCD should be equal to 1.
The GCD of K and L divides D.
The GCD of K and L multiplied by D, this has to divide both A and B. And therefore the GCD multiplied by D has to divide the GCD of those numbers, namely D.
Divides A.
Yeah.
And it divides B. It's got to be less than D.
Yeah, or less than or equal or divides D. It's all, yeah.
Yeah. Okay, well I have a sense there. So GCD KL equals 1 since GCD KL divides D, or times D equals A. And GCD KL times D divides B. Must be less than
I mean,
D.
from this, yeah, it's pretty clear, I would say, that this, because you have some number times D has to be less than or equal to D, and that number is positive, it has to be equal to 1.
Right. Yeah, that does make sense. I see that. Yeah, yeah, yeah. Right. Yeah. Yeah.
Mm.
Okay.
Because now, I mean, I still don't really have fully in my head, but now what we want to show that D is actually equal to A, right? So that is the same as showing that K has to be equal to 1.
K has to be equal to 1.
Yeah. Right? Because K times D is actually equal to A.
Right. Yes. I see. I see. Yeah, yeah, yeah. And how can we show that K equals 1?
Yeah. Okay. Let me think. I mean, I'm thinking of this like as we go, but I think because now we have a pair of numbers, namely K and L, that we might apply the previous exercise to. So this was just so we can like apply the results from the previous exercise.
Right.
So now we can conclude that the GCD of K to the N and L to the N should also be equal to 1. How does this help us?
K to the N. L to the N equals 1. Yeah, using... Apply the previous problem. Yeah.
Let's see. Somehow, of course, we want to somehow use our assumption that A to the N divides B to the N.
Oh, I see what you're going for. Yeah, 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 yeah.
I mean, I don't see it myself that clearly yet, to be honest. But
Yeah, I mean, we... Yeah, that doesn't exactly help because we only have it in terms of K and L.
yeah. I mean, we can write people saying in chat, write A and B as a common GCD, D times cofine parts that we have. Then A to the N divides D to the N. Yeah, exactly. Yeah. Okay. Yeah. Exactly. Okay. We're almost there.
Forces the coprime part k to the n to divide L to the n.
Exactly. So if we now have that, So if we have a to the, because a to the n divides b to the n, we can write like a to the n times some integer r is b to the n. And then we can substitute in our expressions for a and b.
Oops. And our expressions for b are just k. You mean in terms of like k and L?
Yeah, exactly. And then we'll have the d to the n appear in both equations, which we can just cancel out. And we'll get like r k to the n is L to the n. So in particular, k to the n divides L to the n. But now we have a problem because the GCD of k and how did I want to say? The GCD of k and L, k to the n and L to the n are actually equal to 1. So then, yeah, I mean, from that, I think it's pretty clear that k has to be 1, but you can definitely conclude that at least k to the n should be equal to 1.
Right.
And I guess,
yeah.
I mean, it's immediate. I mean, yeah, I feel like they will allow you to say that then k is equal to 1. Well, k could also be minus 1, to be honest.
Yeah.
Yeah, but that, to be honest, that's fine. Did it say something in the exercise about them being positive integers, like your a and b?
I think it did, yeah, actually. Yes, a and b are positive integers.
Yeah, okay. Yeah, then, I mean, so a priori you can say, because, so now what you've written means k to the n divides L to the n, but we know that their GCD is 1, but so their GCD also has to be equal to simply k to the n, because k to the n divides L to the n. So k to the n has to be actually equal to 1. And from that, yeah, I mean, I think it's fine to say that k has to be plus or minus 1. Technically, there should go steps in between there, but I don't know, maybe you've covered this in classes. That's just a bit annoying stuff or boring stuff, to be honest.
Yeah, I mean...
the basic comes down that the integers have only 2 roots of unity. Yeah.
Yeah. Okay, and now that we have, I mean, I feel like we could just say that it's 1 for this case.
I mean, so what you have, k to the n is actually equal to 1. What I mean is that just k is just plus or minus.
Just k itself?
Yeah, because you know k to the n is equal to 1, and therefore you conclude that just k is plus or minus 1.
Right. And then from there, since we have that k times d equals a, d equals a, which implies GCD AB equals a, which implies A divides B.
Yeah. So as you've written now, you should, like in line 76. I mean, you want to say since GCD k to the n L to the n is equal to 1. we have k to the n is equal to 1.
Yes, because using
Yeah, because that's what we use. That's where we use like the previous exercise
right.
to conclude that.
Yes, and then this.
I mean, yeah, and from there we can say k to the n is equal to 1, and from that we can say k is plus or minus 1, and because our things are assumed to be positive, we may actually say k is equal to 1.
Yes.
The chat is being... No, the 67 was not on purpose. I'm too old for this.
It really comes up a surprising amount.
Yeah.
All right.
Exactly. Oh, this was quite an annoying exercise.
Yeah, they made that impressively annoying. Yeah. Yeah, for sure. Oh, I have to get to analysis class. I'm actually late for it.